Okay, good morning. It's Professor David J. De Los Reyes. Okay, the date for this morning will be November 5 and the time is around 1:55 a.m. Okay, my topic for this morning will be a very interesting one. It's the so-called study of alternators. Alternator is the machine that produces alternating current in which that alternating current is the one we are using in our homes. Okay, let's proceed. The topic for tonight will be, for this morning will be a continuation of my long video format discussion in AC machines. I am done with transformer. So for this morning, it will be a new topic, alternator. Alternator is the one that produces our alternating current being used in our houses. Okay, let's proceed. The title of the topic for this morning will be AC Machines, lesson number 53. The first lesson under alternator, and the title of the topic will be alternators. Alternators, or the general term is generator, but when we say generator, it could either be a direct current generator or alternating current generator. Okay, so I will not change that simple, what you call this, conventional naming generator. I will now place the name as alternator. So it should be a generator that produces alternating current. Alternating current. So alternator, a generator that produces alternating current. So if we just say generator, we don't know if the current that it produces will be direct current or alternating current. So to be sure it is an alternating current, we name that generator to be alternator. Okay. What are the main parts of an alternator? The main parts of an alternator, there are only actually, in summary, there are only two. Because to produce an alternating current, I forgot. Hold on, I will get my magnet. To produce an alternating current, there are only two requirements. And in the summary of the requirements that we should have magnetism or magnetic field. And the other requirement is that we must have a conductor. A conductor. Magnetism in conductor. To produce alternating current, it's either that we move this conductor near this magnetism, okay, we produce a voltage across this. Or it could be that we make this conductor stationary, and the one that we will be moving near this conductor is the magnetism. Okay, so it's the other way around. It's either that the conductor will be stationary and the magnetism or magnetic field is the one moving, or it could be that the magnetism is stationary, then we move this conductor across the magnetism to produce a voltage across it. Okay, that's alternator. Okay, so the parts of an alternator, there are only two. The rotor and the so-called stator. For the rotor is synonymous to the word rotating, right? Rotor, the one rotating. So if we say rotor under the study of alternator, it should be the rotating element. Okay? Stator is synonymous to what you call this stationary. So when we say stator, it is the stationary part of an alternator. Okay? And for large alternators, we will just concentrate our study for large alternators. Alternators, the one that produces our alternating current for our household and businesses. We will concentrate our study for big alternators. So it could be the alternator maybe of a big hydroelectric plant, okay, or an alternator of a power plant being fed by a diesel fuel maybe, or it could be an alternator in which the fuel might be nuclear, okay, that's still alternator. That's why they say that the US aircraft carriers are actually don't have to need any fuel for a long time of 50 years because the what they call this, the power generation of that aircraft carrier is being the fuel is being used is actually nuclear, right? So those are all alternators because alternators we need it to move something, right? Like the propeller of an aircraft carrier, maybe to rotate that one, you need a big generator or motor, and for that motor to what you call this rotate, you should have a generator, right? So in the so-called power generation, if the fuel is nuclear, okay, it will take long before you will try to replenish the fuel for that aircraft carrier. That's why they say the Gerald R. Ford aircraft carrier could be replenished, the fuel of this one could be replenished only after 50 years. Okay? Okay, let's go back to alternator. So for alternator, the rotating part is termed to as rotor. The stationary part is stator. And for large alternators, we specify here. The rotor is the rotating magnetic field. And the stator is the one that is stationary, the armature. Okay? It is something like this. The simplest illustration of an alternator is that if we got a conductor which is erected perpendicular with respect to the North Pole and South Pole, it's here, right? And the magnetism of the Earth emanates from the North Pole. It goes to the South Pole. So for this configuration, the one moving here is the magnetic field, the flux of the Earth. That's a natural flux, whether we like it or not. From the North Pole, it goes to the South Pole. That will be applying moving magnetic field. So if you put across it a conductor, whether we like it or not, okay, if you try to place a voltmeter across this conductor, okay, there should be a generated voltage, and that generated voltage is actually alternating current. Okay? So, to produce now alternating current using a generator in which engineers try to design, okay, we must have to bring out some stator annotations and the revolving field annotations. We should know something about them before we could, what you call this, manufacture an alternator to produce an alternating current. So regarding these stator annotations, I just simplify this one, then I will try to discuss it a little bit. Storytelling, guys, because we are discussing concepts over here. There are so much storytelling here, but the story should be the correct one, right? Okay, let's try to bring out the so-called stator annotations. There are 7 annotations here. Stator annotations. Okay. If we try to define stator, it is a laminated steel core. It is something like, it could be something like this, maybe the shape, in which there are slots around. Slots. So they are actually slotted. So assuming this is the laminated steel core, okay, for the stator, it is slotted. Why it is slotted? Uh, there are some openings around in which we place the armature windings. Because we needed armature windings to place on the slots going around, okay, for us to generate a voltage, because the first requirement of a voltage generation is that we should have a conductor. So for this stator, it got some slots going around, then we place so many windings over here, right? We needed the windings so that when we place this winding near a magnetism or magnetic field, we generate a voltage. Okay? Receive armature winding. Okay. The stator is a laminated steel core. It is slotted, and it should receive armature windings. How many windings? Okay. Many turns of windings. It depends on how you design it, or how many turns per slot maybe. So it's a laminated steel core, it is slotted, and it should receive armature winding. And the number of slots, okay, I place it here, number of slots. This number of slots is actually very critical, because we will not just design alternators for a certain number of slots, but there should be a specific number of slots which will give us the correct voltage generated maybe. Okay? And the number of slots, it was specified under the annotation that it should be a symmetrical three-phase. Okay? If you try to construct slots around the stator, okay, just make sure that it should be a symmetrical three-phase. Okay? We are now, what you call this, designing a generator in which this stator, it will come out that the voltage generated will be three-phase. Okay, it will not be single phase, because we are talking large apparent power over here. Large apparent power maybe. The output apparent power of the alternator is actually S, the one we studied under AC circuit or AC machines, right? And for it to be very big, okay, the number of slots should give us a symmetrical three-phase output voltage. There is a certain number of, what you call this, number of slots, which will give us a symmetrical three-phase. It should be three-phase. It should not be single phase, because it's if it is single phase for the meantime, it's not economical. We are talking megavolt ampere here, right? Megavolt ampere. And for number 6 annotations, for us to obtain a symmetrical three-phase output voltage, okay, the total number of slots constructed on the stator divided by the number of poles, okay, times the phases we would like. It should be this should be 3, because we would like it to be three-phase. Okay, if we try to take the ratio slots over poles multiplied by the number of phases we would like, and for here it should be three-phase, so this is times 3. What will come out should be an integer. It should be an exact number. Okay, so this is very critical in the so-called design of an alternator to produce a certain three-phase voltage. The ratio slots per poles times the number of phases should be an exact number. We will visualize this one when we go to the so-called derivation of the voltage generated for alternators, because there are many parameters which are included in the equation for the alternator to generate a voltage. There are so many parameters, right? And the usual voltage generated for stator, it's in the range, okay? The output of the alternator could be, it's three-phase, right? It could be 2,300 volts. It could be 4,600 volts. This is the high voltage. We are on the generator side, alternator side. It could be 6,600 volts, and it could be 13,200 volts. Why is this so? Oh, this is the one we try to step up before going to the transmission line, right? Before we put the voltage over here, it should emanate from the generator before we feed this to the transmission line, right? Okay. So if we feed 2,300 here, it's not so much because this transmission line is actually very low. If this transmission line is 500 miles and you feed only 2,300, okay, before it reaches 500 miles, maybe the voltage is too low already. So it's possible that we will be using 13,200 maybe. But this 13,200 is still very small. So actually, before we feed to the transmission line, there is a step up transformer. We will step up this one. Okay? It could be the primary of the transformer is 2,300, but before we will feed to the transmission line, we will be using a step up transformer. Maybe the ratio of transformation is 50 times. So if we try to multiply this by 50 times, this is very big only, 2,000. It's almost 100,000 already, right? And it is feasible that we could feed this 100,000 volts to the transmission line. Okay? Then it travels 500 miles. This 100,000 is still very big. Before we will step down this one to go to the secondary fuse, and which again we will step down that voltage to a value 230 or 115 that it will be used by our household clients or businesses. Or that's how we generate voltage. So I am telling you now, under the stator annotations, the voltage generated by the alternator could be 2,300, 4,600, 6,600, and 13,200. And these voltages, before we will feed it to the transmission line, we will feed this to a step-up transformer to increase the value of this, so that when the voltage will travel 500 miles or longer than that one, there will still be a big voltage at the far end in which clients will try to use it after stepping it down. Okay, that's the so-called stator annotation. Okay, I will repeat it. Stator is made of laminated steel core. They are slotted. Okay, these slots receive the armature windings. The armature winding is actually the conductors needed so that when the generator rotates, it cuts the magnetic lines of force, so it will generate voltage. And this number 5 here, the number of slots is critical because we will be making number of slots in which the output number of phases will be symmetrical three-phase. And for it to be symmetrical three-phase, the slots per force times the number of phases should be an integer. Okay? And we are sure that the generated voltage will come out to be 2,300, 4,600, 6,600, or 13,200. It depends on the total number of turns of the windings that we will be placing on the slots. Oh, that's stator annotations. Or at least we now know what is a stator. A stator is just a round thing made of laminated steel core. It got slots, and which these slots try to receive armature windings, many armature windings. So if it's a big transformer, there will be thousands of windings with it, in which the, what you call this cross section should be very big. If it carries a very big current, the diameter should be very big. So actually, in the so-called manufacture of alternators, it's very expensive. Okay, let's try to discuss the annotations for the revolving field. So, stator is actually the part of the alternator in which the windings are wound, okay, to generate voltage. It's the carrier of the armature winding, that's the stator. How about the revolving field annotations? Why revolving? It's something like this. Number one, the number of fields should be an even number. Okay, it should be an even. The requirement for the number of fields should be an even number. So the least number of fields should be 2. It could be 4. It could be 6. Could be 8. A multiple of 2. That's the requirement for revolving field. And what is the use of this revolving field? The revolving field is actually where we produce the so-called, we place the exciting current. No, exciting winding. What is exciting winding? To produce a magnetism, okay, we should have an iron core, then we place a winding on it, wound the winding. Then we'll try to energize. Energize meaning inject a current. Okay? So if there is an iron core and there is a winding wound around it, okay, we will be producing a magnetic field or flux. And this flux is actually revolving. Revolving, it seems like it's moving. Because if this is north and this is south, okay, we use the right hand rule here, right? The curling of the hands goes with the direction of the current, and the thumb points to the direction of the flux produced. So with this configuration, this will be north, okay? The current is downwards. The thumb shows the direction of the magnetic flux, it is this. So if this is north, this will become south. So whether we like it or not, if this winding is energized and so with this, the flux will emanate from here, it goes here. Okay, and the stator is actually in between, right? In between the flux. So if we try to rotate this stator here, right? It will cut this magnetic line of force or magnetic field. Okay, there is an interaction of the winding and the flux, so we will generate a voltage. Okay, there will be a voltage generated. Okay, because the requirement for a voltage generation is that there should be a moving flux, okay, and a conductor that will cut this moving flux, right? So when this is revolving, we term this one, it's not really revolving that it rotates like that. It will just emanate from the North Pole, goes to the South Pole, and in between the middle of it is actually the stator, a winding. So when this winding or stator is actually driven by a prime mover, okay, it should be driven by a prime mover because there should be a movement, right, of the winding to cut the flux. So the interaction of the flux and the winding will generate a voltage. Okay? So this right hand rule here is very important. Okay? For a generator, for the right hand rule, the curling of the hands goes with the direction of the exciting current, and the direction of the thumb points to the direction of the magnetic flux produced. Oh, that's a revolving magnetic field. Okay? And also, as a final illustration, it's the magnetic field of the Earth. It emanates from the north, it will go to the south. So if you place a conductor, stationary conductor, okay, whether we like it or not, the flux is moving, it cuts this conductor, there is an interaction. So if we place a voltmeter across this conductor, which is stationary, okay, there should be a generated voltage, and that generated voltage is actually alternating current and nature. Okay, guys, that's the initial concept on how to study alternator. At least we now know what is an alternator. It is a machine that converts, or what you call this, produce alternating current. And what are the requirements in order to produce alternating current? There should be magnetism or flux or a conductor. It could either be that the conductor is stationary or moving. For the flux, it could also be stationary or moving. Okay, good morning from Los Angeles. This is Professor David Jedler.